Hello, today's topic is concept of stress. I am aware that most of you are under a lot of stress due to the seemingly never-ending stream of assignments and tests. However, in this topic we are not discussing this stress. Rather, we are discussing the stress from the point of view of mechanics of materials. This topic has 5 parts. The first of which is introduction to normal and shear stress, which we are going to discuss now. So let us start. Before we start, it is important to know that to understand the concepts of stress, you should have prior knowledge of equilibrium of bodies. In other words, if you are given a frame or a truss with some applied loads, you should know how to calculate the reactions in different members. If you are able to do that, then you are all ready to start this very interesting topic of concepts of stress. Now, imagine that a body or a truss as shown in the figure is subjected to a point load at Q, and we want to find out what is the reactions at LM, LP and KP members. So how will you do that? You are most likely going to draw a section, imagine that you have broken your frame in truss into two, and using basic equations of equilibrium you can calculate the reactions in different members. Most likely, if you have done it correctly, these are the answers you can expect. So far so good. But now the question is it enough to calculate the internal reactions in different members? Will you be able to design a truss simply by the knowledge of different reactions in different members? For example, imagine that the same truss was made once out of wood, the second time out of steel. Everything is same, the geometry is same, the loading is same, everything is same. Do you expect both the wooden and the steel truss to react in the same manner? The answer is no. By intuition, we know that the structures are going to behave differently when subjected to the same load. Also, another important point is when you solve problems of truss like this, it was mostly two-dimensional. So, does not the thickness through the screen thickness matter? Of course, it does. So, these are some of the questions that we will try to answer. So, let us start. In the member LP, we found out that the load was 1050 kilonewton, and then we know that the stress is defined as F by A, where F is the load, A is the cross sectional area. Load and the cross sectional area are normal to each other. This is definition of normal stress. The unit of stress is Pascal. 1 Newton per meter square is 1 Pascal and 1 Newton per millimeter square is 1 megapascal. Be very careful about the length unit that you use. Try to be consistent throughout the choice of the problem. 1 megapascal or 1 Newton per millimeter square is by far the most commonly used unit. Stress is denoted by Greek letter sigma. And the force can be normal or tensile depending on whether this load has a tendency to pull the member LP to a longer length or make it slightly shorter. Meaning, if the force is pointing away from the body, then that is tensile stress. The reverse is compressive stress. In both the cases, the definition of stress is still F by A and it is still denoted by Greek letter sigma. Also, very important to understand that F by A is not stress at a point, it is the average stress over the entire cross section. The correct definition of stress at a point is delta F divided by delta A, where delta A tends to 0. This gives me stress at a point. Now, imagine that you have a body which has uniform cross section throughout, subjected to load at the tips. No, if you make a cross section somewhere at the bottom, this is the variation of local stresses at a point you can expect. And similarly, at different sections, you will have slightly different variation of stress. Now, the question is then, how do we calculate this variation of stresses? The answer is, sadly, we cannot calculate this variation of stresses analytically. So what we are going to do is we are going to calculate the average stress over the entire cross section. The value of that is F by A. So throughout this course, we are not actually trying to determine the stress at a point because we don't have the mathematical tools to get there yet. But we calculate the average stress throughout a cross section. So it is F by A, not delta F divided by delta A. So let us look at a problem. This is a very simple problem where I have a plate where there are some holes and voids that have been made. So a circle has been punched at C, a semicircle has been cut out at A. This is subjected to load P is equal to 25 kilonewtons everywhere. What is the stress at section A, section B, section C? Should it be the same? Should it vary? How will it vary? Let us try to find out. So let us try to solve this problem. A 10 millimeter thick steel plate, various holes as discussed. Let us try to calculate the stresses in different sections. Start with AA. At section AA, the load is 25 into 10 to the power 3, which is the same everywhere. Then the cross-sectional area is thickness 10 into 10 to the power minus 3, but the width is not 25, it is 25, which is the overall width minus the radius. So it becomes 25 minus 5 is 20. So you get 125 megapascal. Similarly, in section BB, you are getting load 25, which is same, 10 thickness, which is same. Cross section is 25 because there no hole or discontinuity across this section. So the stress is 100 megapascal. Finally, CC, you have 25 load, 10 thickness, which is same. The width is 25 minus radius of this hole, diameter of this hole, which is 5. So you get the answer 125 megapascal. Keep in mind that all of these quantities 125, 100 are average stresses across the entire cross sections, not necessarily stress in individual points. But now the next question that comes to our mind is, okay, normal stress is when the load is perpendicular to this cross section. What happens if the load is parallel to the cross section that I am interested in? For example, let us draw the free body diagram of this bolt. It will be something like this. It has reactions F and F prime. Now, what about the cross section EE prime? What is the stress in this cross section? Can I call it normal stress? The answer is no. Normal stress, as previously defined, is when the load and the cross sectional area are perpendicular to each other. In this case, the cross sectional area and the load are parallel. In such cases, the body is said to be subjected from shear stress. Shear stress is denoted by Greek letter tau. Unit of shear and normal stresses are the same. So for this, the cross sectional area of a bolt is a circle and tau is F by A prime. Another example of shear stress is, imagine that you have a plate which is subjected to two loads as shown, P and P prime. If I make a section at C, let the cross sectional area be A, then tau is P divided by A. Okay. The third type of stress that we are going to learn about is bearing stress. Bearing stress happens when you have a structure where you have basically two plates and a bolt. Now, what is the load that this bolt is transferring to the plates? Okay, so you can imagine that if from the top view of this bolt looks something like this, and if the load is large enough, you can expect some sort of damage like this. So what is causing this damage in this plate? What is causing the whole of the plate to increase? This is bearing stress. How do we calculate bearing stress? We do the following. So imagine now we are looking at this part of the plate. This is subjected to normal load at every point as shown in this figure. E- Equivalent force of this is that instead of this curved semicircle with radius d, I am replacing it with a single line of length d, and all of them are subjected to normal forces. So it turns out that both of these are equivalent to each other, and therefore sigma b, or the bearing stress, is P divided by A, where A is diameter into the thickness. This is bearing stress. To understand bearing stress better, you can do a small experiment in your house. Take a paper, punch a hole inside it somewhere, put your pencil through the hole, and hold the paper from both ends and try to remove the pencil away from the hole. You will see that you are applying the load on the pencil, but the paper is getting subjected to compressive stress and is tearing apart in the region which is very close to the paper. This is known as bearing stress. Bearing stress can be imagined as a special case of compressive stress. It is not like that the bearing stress is only subjected when you have a circular object or when you have pins. It is also possible when a situation like this happens. Imagine that you have a concrete tile or a platform. On top of that there is a wooden block, and on the wooden block a load of 4 kilonewton is applied. Now in the region where the wooden block is sitting on top of this concrete block, due to this load 40 kilonewton, the concrete block is going to be subjected to some compressive stress, that is bearing stress. We call it bearing stress because this is arising due to the fact that my concrete is bearing the load applied to the wooden block. So sigma B in this case would be 40, which is the applied load, into this area where the load is being beared, that is 120 into 100 megapascal. So with this we end our first topic. Thank you.